Okay, I will tell you about eigenvalue estimates for p-Laplace problems. And in the first part of my talk, omega will be a bounded Lipschitz domain in Rn, and p is a real number greater than 1. We are interested in this eigenvalue problem for the p-Laplace operator, which is as usually denoted by delta p. This is defined, as everyone knows, like as the divergence of the modulus of the gradient of u to the power p minus 2 times the gradient of u. And we consider homogeneous Neumann boundary conditions, and here μ stands for the outer unit normal to the boundary of omega. Clearly, 0 is an eigenvalue and has corresponding eigenfunctions that are constant in omega. We are interested in the first non-trivial eigenvalue that can be variationally characterized as follows. μ1 from now on is the minimum of the Rayleigh quotient between the LP norm of the gradient of phi to the power p over the LP norm of phi to the power p, where phi is a test function which belongs to the Sobolev space W1p of omega, is not identically 0 and has 0 mean value, in the sense that the integral over omega of phi to the power p minus 2 times phi is 0. Clearly, the right power of μ1, which is μ1 to 1 over p, coincides with the best constant in this Poincare-Wirtinger inequality, which holds true for every phi in W01 in W1p of omega. The problem is that the exact values of this μ1 are known only for really specific values of p, more or less p equal to 2 when the p-Laplace operator coincides with the classical Laplacian, and something when we are in limit cases like p equal to 1 or p equal to infinity, and for very special domains like bores or rectangles. And so it is natural to look for estimates, and hopefully sharp estimates, for this μ1 in terms of simpler geometric quantities related to the set, such as measure, perimeter, diameter, and so on. So we can distinguish between upper bounds and lower bounds for μ1. And I just want to recall you two very celebrated inequalities. The first one is an upper bound, and this is the isoperimetric inequality known as the Zygov-Weinberger inequality, which holds true when we deal with the case p equal to 2. So we consider the classical Neumann Laplacian, and if omega varies in a class of sets with fixed measure, then μ1 is maximum on balls, and the equality sign in the inequality holds if and only if omega is a ball. This inequality has been proved first by Zigo in 1954 using conformal mapping techniques, a method that nowadays is called method of conformal transplantation, and its validity was proved for simply connected domains in R2. 2 years later, Weinberger introduced a completely different method that allowed him to get this result in the full generality in Rn without any restriction on the geometry of omega. And the Weinberger's technique has also the advantage that it has been adapted in very different contexts to establish isoperimetric estimates for eigenvalues of linear and nonlinear operators, also combinations of eigenvalues of the Laplacian with Dirichlet or Neumann boundary conditions. And here you can see just a short list of many authors that in the last decades have been inspired by these kind of arguments. Just a few remarks on this celebrated inequality. The first one is that actually Weinberger noticed that in the proof, in the paper by Zigo, the authors prove more. And indeed, he proved that the sum of the reciprocals of the first two non-trivial Neumann eigenvalue of the Laplacian is minimal on balls. And this inequality holds true again for every simply connected planar domain. And since on a ball we are in 2 dimensions, so on a disk, the first eigenvalue is double, which means that μ1 of B coincides with μ2 of B, this inequality implies immediately the previous one. Just a few remarks on this inequality. One, there is a quantitative version of this inequality, or if you want, a sort of stability inequality, which was proved by Nadirashvili in 1997. And Nadirashvili proved that actually there exists a constant, a positive constant C, such that the difference of the two terms on the right and the left-hand side of 1 is greater or equal than C times this quantity A of omega, which is defined in the slide and is called the Frankel asymmetry, is the infimum between the ratio of the measure of the symmetric difference of omega and B over the measure of omega, where B is a ball having the same measure as omega. And somehow the Frankel asymmetry measures how far omega is far from being a ball. In turn, this inequality 1 can be sharpened, and indeed, in 1971, Hersch and Monkevitz shown that there exists a positive constant such that if omega is a planar, simply connected open set, then we can add in the sum another term, which is C over lambda 1 of omega, where lambda 1 is the first eigenvalue of the Laplacian operator with Dirichlet boundary condition. If we look for the higher dimensional analog of this inequality, then we have to consider this inequality, which has been conjectured by Oshborg and Ben-Gurion in 1993, where we have the sum of the reciprocals of the first n non-trivial eigenvalue of the Neumann Laplacian. And the Oshborg and Ben-Gurion, they conjecture that this sum is minimal on both, having the same measure as omega again. But as far as I know, this conjecture is still open. And recently, in 2018, Wang and Xia made a step forward, the full conjecture, by proving that actually the sum of the reciprocals of the first n minus 1 eigenvalues is minimal on both. And the equality sign holds if and only if omega is a ball. If we want a quantitative version of the original Zygmunt-Berger inequality, then we have to wait until 2012, when Brasco and Fratelli proved this quantitative version, where here in the right-hand side, we see a positive constant C times, again, the Frankel asymmetry to the power 2. And what is really interesting here is that the exponent 2 is proved to be sharp. And actually, the authors said in the paper that this is the most difficult part of the paper, because what happens is that mu1 of B is multiple, and so the shape functional which maps omega into mu1 of omega is not differentiable near the ball B, which is the optimal set. The problem is that all the things that we have discussed about Zygmunt-Berger inequality crucially exploits some peculiarities of the Laplacian. First of all, the linearity of the operator, and then the knowledge of the explicit form of the eigenfunctions on both in terms of Bessel functions. These two things are not valid when P is different from 2. And again, as far as I know, the Zygmunt-Berger inequality for the p-Laplace operator when P is different from 2 is still an open problem, except for some partial results for convex domain when P is equal to 1 or P is equal to infinity. If we consider upper bounds, I think that the most celebrated one is due to Penny and Wamberger. They proved in 1960 that if omega is a convex bounded domain, and again we are in the linear case, so the first non-trivial of the Neumann Laplacian is greater or equal than pi square over the diameter of omega to the power. The Penny-Wamberger inequality is sharp, since the product between mu1 and the diameter of omega to the power 2 goes to pi square for a parallelepiped all but one of whose dimensions shrink to 0. But differently from the previous Zygmunt-Berger inequality, there are the generalization of this one to general P, and you have here a list of many papers connected with this kind of argument. For example, when P is equal to 1, P is between 1 and 2, P is greater than 2, or P is infinity, or in the anisotropic setting, or on manifolds with non-negative rich curvature. In any case, in this kind of inequality, we cannot drop the assumption of convexity, and to convince ourselves, it is enough to consider the classical example of a planar domain made by two equal squares connected by a thin corridor, since in this case, this quantity can be small enough in order to get this inequality not valid anymore. So if we want to consider non-convex sets, we have to deal with the new quantities other than the diameter. And I am going to show you this first inequality, which is contained in this paper written in collaboration with Francesco Chiacchio and Cristina Trombetti from the University of Naples, Federico II. And this inequality involves the so-called best isoperimetric constant relative to omega, which is defined here. This Kn of omega is the infimum over the over E, the subset of omega, between the perimeter of E relative to omega and the minimum between the measure of E and the measure of omega minus C to the power 1 minus 1 on N. This constant obviously is always less or equal than the classical isoperimetric constant, which are equal here, and omega n stands for the measure of the unitary ball in Rn. And this quantity is strictly greater than 0 when omega satisfies a second property, and this is always true if omega is a Lipschitz domain. So if we have a bounded Lipschitz domain, we can prove that μ1 is greater or equal than this constant, depending on P and N and Kn, times another quantity that can be read as the first Dirichlet eigenvalue of the p-Laplace operator in the ball omega sharp having the same measure as omega. Moreover, this inequality is sharp, at least if we are in the linear case and in the planar case. Indeed, if n and p are both equal to 2, then our estimates can be explicitly written in this way, where here we recognize the first 0, J01 of the Bessel function of the first kind J0, because as everyone knows, the first eigenvalue of the Dirichlet Laplacian in a ball is written as the ratio between J0 square and the radius of the ball to the power 2. If we want to prove that this inequality is sharp, we can consider a sequence of rhombi of omega m having for simplicity side 1 and acute angle beta m vanishing as m goes to infinity. And we can compute the measure of omega m and, what is important, the best isoperimetric constant relative to omega m, using some results contained in this beautiful paper by Andrea Cianchi in 1989. And with a little effort, we can prove that the limit of μ1 is equal to J0 square, so that at the end, we have this chain of equalities and we have the equality sign in our estimate. Just another remark is that actually if omega is convex and symmetric about a point, then somehow we can improve the Penny-Weinberger inequality. And indeed, we can again compute the best isoperimetric constant in terms of the width of omega and its measure. And in this case, our estimate reads like this. And so if we suppose that omega satisfies this inequality, which means that the set has to be small enough, then we have an improvement with respect to the classical Penny-Weinberger inequality, because we can add on the right-hand side this delta omega, which is strictly positive. In the second part of my talk, I would like to focus on the non-convex setting, and just understand how the results I'm going to talk about are inserted in literature. I just wrote here a list of papers connected with estimates of Neumann eigenvalues. Of course, this list is far from being complete, and we can start from the celebrated monograph by Catherine Brandolini in 1980, where the author considered weighted Neumann eigenvalues with a weight on the right-hand side of the equation. Then we can go on with one-dimensional problems with the different powers in the Rayleigh quotient between the norm of the derivative and the norm of the test function, or estimates on triangles, estimates for Hermite operators, and so on. We can make some consideration on these papers by Burenkov, Goldstein, Hukloffen, Zelintsev, and many authors, where they use a quasi-conformal mapping technique in order to have lower bounds for Neumann eigenvalues of the p-Laplace operators. Here I want to show you some results contained in these two papers written in collaboration with Francesco Chiacchio and Emily Dryden and Jeff Langford from the Bucknell University in Pennsylvania. So we are dealing with no convex sets, and I will focus on planar sets with an axis of symmetry that I can choose on sides with the vertical axis. So just to set the scene, I consider a curve gamma of S that is a smooth, simple, non-closed curve parameterized by its arc length, which means that capital L is the length of the curve. And we can suppose that this the image of this curve is symmetric with respect to the vertical axis, which means that the function x is odd with respect to L over 2. And we consider this kind of sets. They are constructed via Fermi coordinates using gamma as a frame of reference, which means that if delta is a smooth function that we suppose even with respect to L over 2, we can construct our set in this way. We fix a point on the curve, and then we move orthogonally to the curve by a distance delta. And the domain can be explicitly written in this way. Just to make the following theorems more clear, I just want to fix some notation. And so D is our set in Rn, and df is the set described in Fermi coordinates, which means that df is a sort of rectangle, and actually it coincides with a rectangle when delta is constant. And we always assume that the Fermi transformation is one-to-one from the closure of df to the closure of D with a positive Jacobian, which coincides with one plus r k of s, where k of s denotes the signed curvature of gamma s. Some natural questions arise when one deals with this class of sets. The first one is that if we have a symmetric set, is it true that μ1 has a corresponding eigenfunction which is symmetric with respect to the vertical axis, which is odd with respect to this axis? We can answer to this question with a positive answer, at least when p is equal to 2 and the set is thin enough. So I will write μ1 equal to μ1 odd, and this means that μ1 has a corresponding eigenfunction which is odd with respect to the vertical axis. And what we can prove is that this equality holds if one of the following alternatives holds true, depending on the sign of the curvature k and on how thin the set is. Indeed, in a few moments, I will show that these strange inequality written here are actually explicit geometric criteria that allow us to understand when μ1 is equal to μ1 odd. And in order to convince you about this, let me just recall that μ1 by definition is the minimum of the Rayleigh quotient. And so if we want μ1 to be less than something, we can choose a suitable test function phi and assume that the Rayleigh quotient of phi satisfies this less or equal than. Of course, this means that the geometric constraint that we are imposing on set will depend on the test function. And for example, if we are in a very simple situation with delta constant and we test μ1 with a very simple function, which is x, which is odd with respect to the vertical axis, if we are in the first case, when k is greater or equal than 0, then there exists an odd eigenfunction corresponding to μ1 whenever the maximum of delta square times 2 plus delta k square is less or equal than the ratio between the momentum of D and the measure. When P is different from 2, the situation is a little bit more complicated. Just a few remarks. First, when μ1 coincides with μ1 odd, it is very easy to prove that μ1 is simple. On the other hand, if P is different from 2 and μ1 is simple, we can prove that μ1 coincides with μ1 odd. And summing up, we can say that proving that μ1 has a corresponding eigenfunction which is symmetric with respect to the vertical axis is equivalent to proving the simplicity of μ1. And we can say some words when the set D is thin enough by using by studying the asymptotic behavior of the μ1 when the delta function goes to 0. If I have time, I will tell you something at the end. But I want to go on with this estimate because our plan was to prove a lower bound for μ1, and we just move to μ1 odd for a moment, because if we have an odd eigenfunction, it's not so hard to prove that if delta and either delta k or delta square k are concave functions with the derivative of delta less or equal than 1 in modulus, then there exists a constant Bp whose values is explicitly written here, such that μ1 odd is greater or equal than Bp times the ratio between pi p and the length of the curve to the power p, where pi p is this number, and it coincides with the pi when p is equal to 2, is a sort of a generalization of pi, and it is introduced in this paper by Lindquist in 1995. This is a paper about the functions cosine p and sine p. Somehow this is an estimate which reminds the aspect of the Penny-Weinberger inequality, but it also, I stress it, in non-convex setting. So if we put together the two previous theorems, we have that if P is equal to 2 and the domain is thin enough, then μ1 coincides with μ1 odd is greater or equal than a constant time pi square over the length to the power 2. And this estimate is sharp since the equality sign holds here when this is a rectangle, which means that gamma is a segment with curvature k equal to 0 and delta is constant. I don't have time to bore you with details of the proof, just a few words. I would like to say that the main steps are these two. We first divide D into thin slices parallel to gamma, on which the considered eigenfunction has a 0 mean value. And then, since these slices are arbitrarily thin, we have a one-dimensional problem, and we can estimate μ1 odd from below in terms of the first non-zero eigenvalue of a one-dimensional weighted p-Laplace problem. I will end my talk, I don't know if I have another couple of times, yes, probably, with some examples. So the first one is this. We can build this kind of set starting from an arc of catenari. And since k is positive, we can enlarge in this direction by any distance delta. For simplicity, suppose that delta is constant positive. And if A is small enough, in this parameterization of the arc length with respect to its, in this parameterization of the catenary with respect to its arc length, we get that the delta is the curvature is concave. So we can prove that if delta is small enough, μ1 coincides with μ1 odd, and is greater or equal than this explicit number where delta and A appears. An analogous An analogous example is the following one. We can construct an annular sector with radii r and r plus delta, with theta between pi over 2 minus theta tilde and pi over 2 plus theta tilde. And again, if delta is small enough, and we have explicitly how small delta has to be, then we have that μ1 has a corresponding eigenfunction which is symmetric to the vertical axis and is greater or equal than this explicit number where we have no use of the Bessel functions. Finally, we can construct this example that we call the Handlebar mustache by considering the following concave function which is piecewise linear and changes its sign in the interval 0, 1.6. And as everyone knows, up to a rotation and in translation, there exists a unique curve gamma parameterized by its arc length having k has curvature. And we can suppose by rotating and translating that the image of gamma is symmetric with respect to the vertical axis. And so we can enlarge the curve building this Handlebar mustache domain. And if delta is small enough, again, we know that μ1 has a corresponding eigenfunction which is symmetric with respect to the vertical axis, and we have these explicit lower bounds. I think I don't have any time. Is it true? Yes. So I thank you very much. I stop here. Oops. Thank you for your attention.